All right, so we stopped the last video right here when we got this general expression for beta. And we're going to use that general expression for beta to find a general expression for power. So please look at your notes. This is slide 8 in your notes. And this is the general expression for beta that we got, okay, from those notes. And then we're just doing some simple things in here that you can probably follow along, but just really quickly, we're rewriting this as a cumulative distribution function, right? Instead of z less than or equal to z1 minus alpha, we can rewrite it as phi of x, okay? So we rewrote beta as a cumulative distribution function. And then since power is 1 minus beta, we're going to take 1 minus that expression. And we know that 1 minus phi of x is equal to phi of minus x, so we make that change. And then we also know that z of alpha is equal to 1 minus z1 minus alpha, so we make that change in here. And our expression depends on here, on these bottom two lines, it depends on if mu1 is greater than mu naught or mu naught is greater than mu1. And when we look at over here on the board, right, we had mu1 greater than mu naught. But it could easily have been the reverse situation, right? This could have been mu1 over here, or the alternate hypothesis, and mu naught could have been over here. In which case, we come up with a different expression for beta, which would have been mu naught greater than mu1 on the bottom. Okay, but of course, like a lot of times what we do is to take care of those differences with the absolute values, right, so that we can consolidate into one expression. So this is slide 10 for you. Okay, so this is our general expression for power now where we've used absolute value. And so a couple key terms here is that when we have the difference in these two means, it's called the effect size. All right, that's the effect size. So for the example in class that we did, we could go ahead and put in our numbers, not in class, but the example I just did in the last video, we could put in our numbers and we could find the same thing that we found for the power before. Remember the beta was 0.1963 and 1 minus 0.1963 is 0.0837. So we get what we stated we should have. Okay, so that's our general expression for power. And I want to point out, remember that it is for a one-sided alternative, right? We were just looking at a one-sided hypothesis test. But we also have to look at two-sided. And we'll do that in a minute. I just have a couple questions, for you to contemplate before we do that. So I told you this before, but I want you to think about it one more time. So what would happen to the power now? I talked about beta, but what would happen to the power if we decrease alpha? So if we decrease alpha, say we set it at 0.01 or something, our upper bound now would shift. It'd be greater than 53.29. It'd be here someplace, right? You can automatically see then that this area is going to decrease. So if we decrease alpha, the power is going to decrease as well. And in your notes, I've asked you to find beta and the power of alpha equals 0.01. So you should be able to follow along that and just make sure that you can prove to yourself that those are true. And then I just wanted to ask you one more question about what would happen to the power if the effect size is greater. So remember, the effect size is those difference in the two means. And I just wanted to draw this on the board for you. So let's look at it over here instead. I'll try to keep with my same colors if I could find them. So like here then, here I could draw H naught, okay? And if my effect size is greater, that means I have a bigger difference in these two means. So that my distributions are going to be much more separated in space, right? Let me kind of, let's just finish that off. And then let me draw this one that would be much further away. They're supposed to look like the same distribution, the same shape of those distributions, and I didn't do that very well. So let me just get that here a little bit. Okay, so those are supposed to be the same two shapes. And now, and here would be mu1, and then over here would be mu0, and here would be mu1. So the effect size is much bigger. They're separated in space more. They have a lot less overlap. Okay. not getting that very well. I'm sorry, I'm on an angle here. But you could see, like, we could say, like, well, so what is the alpha error in this case? Like, maybe here is 0.5% or so. Okay, so this would make this the accept H0 region, and over here is the reject region, right? Reject H0 region. So if we were to look at that beta error again, that it means that when HA is true, which is this green shape, how often are we actually accepting H0? So green is true, how often are we accepting H0? It's this little tiny area right here, okay, really small. So our beta area is now smaller when effect size increases. And that means that our power, which is all this area, is increased when the effect size increases. So the errors come about because of the overlap. And so the more we can reduce that overlap, then the less alpha and beta errors will have, higher the, well, I shouldn't say alpha, but the lower the beta error will be, and then the higher the power will be. Okay, so that is looking at a one-sided alternative. These same principles about, if we decrease the overlap, they also apply for a two-sided alternative. If we increase n, if we increase the sample size, we're also going to reduce the overlap, right? Because once we reduce effect size, we have sharper, steeper curves for the sampling distributions, the sample means. And so that will also serve to increase power. And that is something that's definitely within our control, right? We can increase sample size if we need to. Of course, it's time and money, but it's something within the experimenter's control. We're going to go now to looking at a two-sided alternative. And I think what I'm going to do is go now to a different video. And I'll wrap that up using the slides that you have in front of you, or hopefully in front of you. Okay, so I'll see you in one more video.